Hello boys and girls, today we're going to talk about one of my favorite things, the hot plate. What I'm about to do is plug in this hot plate to a kilowatt power meter. But before I do so, I want to record— Dang it! You can't put an announcement on when I'm making videos. Thanks. First, I want to note the voltage of the outlet when the appliance is off. So that would be unplugged. And I'm only going to do 3 sig figs here. So I'm going to call this 120 volts. Cool? And then I'm going to plug this sucker in, and I've already turned it on. And I want you to notice that the voltage will drop. Oh my goodness, that sucker dropped. I'm going to say the voltage on then is 113 volts. You see what I'm saying? But what stuns me is I can unplug this and it'll go back up to 120 again, all right? You see 120, and that I'm gonna call the voltage when there's no load, but the voltage is dropping when there is a load because I've got something like internal resistance. It's equivalent in concept to the internal resistance of a battery. So there's some pushing that the utility is doing, and I guess the utility is mostly doing that pushing at the transformer, or maybe even earlier in the power generation. But let's think about the transformer as a place where the utility is putting out 120 volts. So if there's no load, then I'm also going to see 120 volts because there's no current going through that internal resistance to drop our voltage. But as soon as I put on a load, I put a resistor out here, that draws a current through the wires that are leading to this location, which means there's a voltage drop across those wires. And that's the concept we're going to try to tease out today. What I find really powerful is plugging it into here. You have to make a prediction. If I plug into here, is the voltage going to drop or not? And here we go. We'll test that out. It seems— Holy cow, the voltage dropped to 113 volts whether I'm in here or in here. And that's because these two outlets are in parallel. I'm seeing that the voltage drop between the hot and the neutral locations is 113 volts right now. And wow, that is a hot plate, holy cow. And right now, that voltage drop is only, well, it is up to 120 volts. So something's going on with internal resistance that's causing that. And I want to take one step further. I'm going to move my hot plate aside because it's really hot, but we're going to continue using it. I got to give you a little bit of background first. I've got this connected to an extension cord that is something like maybe 15 meters. I didn't measure it very carefully. Now I'm going to go to fast forward while I disconnect, watch as I disconnect this connection and put in another 15-meter extension cord. So what I'm doing is I'm effectively adding more internal resistance by putting in this junky extension cord that you'll see in just a moment. Please enjoy. So my plan now is to turn on the hot plate again. Watch this. I've got the hot plate, and notice still the voltage when it's off is 120 volts because, well, we really didn't affect the fact that we've got parallel conductors, we've got additional conductance leading to there, but there's no voltage drop because there's, at this point, extremely small current going through them, so there's no voltage drop in the additional significant, watch how significant it is. It's a significant resistance because while I plug this in now, the voltage is not going to drop to 113, it's going to drop to freaking 108. That means I've added additional resistance in this honkin' 15-meter junky old wire, and that additional resistance has caused a voltage drop. So remember, you can't trust the voltage reading on a wire when you plug in the outlet without a load to be the actual voltage when a load is in operation. So we're going to go a little bit further with this. So bear with me as we do a few calculations, but I'm going to get this hot plate way out of the way first. I'm going to do the calculation without the additional 15-meter in there because we see enough internal resistance in this case right here that we can still make some calculations and learn some stuff. So with voltage off and voltage on, I'm going to call this the voltage difference between the hot conductor, and it's AC, so that's making everything a little bit more complicated, but we'll just pretend that it's DC, or we can work with RMS or whatever you want to do. But I'm calling this, think about this as the hot conductor, and this is the neutral. For our purposes, at least, we can call this neutral the same thing as the ground. And they're subtly different, and that's worth a whole bunch of other videos. But this is ground, and it's sort of like the earth. And in rural situations, sometimes they just distribute a single wire that's hot. So what I'll do with this hot wire, and remember, the hot wire is coming over here, and it's going to some resistance. That's my hot plate, right? That is my hot plate right there. It's cool how the hot wire serves the hot plate. Yeah, everything is hot here. Good. And boy, we're getting into summer. All right, all right, all right. Check this out. Hot versus neutral. That voltage over here, if I connect to that wire and to that wire right there, I'm reading 120 volts. But if I connect right here, the voltage between there and there is only 113 volts. And I'm arguing that if I could go over to the transformer that my power utility owns, I could still measure 120 volts over here. So something's happened between here and here. And I like to pretend that wires don't have any resistance, but clearly this length of wire does have some resistance and has caused a voltage drop across the wire. It's a subtlety we have to understand. This voltage drop is happening across this wire right here, and we can say the voltage drop is the current through the wire times the resistance of the wire. And what I didn't get for you is the current across, the current through my, sorry, the current through my hot plate. So let's get that right now. It says 8.40 amps. It says 8.40 amps is the current. And what I want you to note is that that's going to be the current through this conductor, and it'll be the current through the hot plate, and it'll be the current back on the ground, I suppose, wherever dirt is, whatever. But by the principle of diarrhea, this has to be the current throughout the entire thing. So I've got that current, 8.40 amps, and I've got a voltage on and a voltage off. So maybe the first thing that we should do is figure out what the resistance is of my hot plate. Because hooking up a hot plate caused a current to go, and that current depends on the voltage that the hot plate's seeing. So a first approach, you might want to take the 120 volts and say some Via's IR business right there. You could take the 120 volts and try to solve that for current. But I think what might be more appropriate is the current. And, oh, sorry, we know the current. We're trying to find the resistance of the hot plate. It might be more appropriate to say it's the voltage while it's on, because that is actually the voltage drop across the hot plate. And then that'll be divided by the current in the hot plate. I'll just call it current hot plate. Now, the current's going hot plate? Wow, hot plate. How about that? The current through the hot plate. It is, trust me, it's a really hot plate. We can find that. We can take the voltage on, which is 113 volts, and we can divide that by the current while it's on, 8.4 amps. And I'm finding that the resistance then, let's get the resistance of the hot plate. This is the resistance of the hot plate because we've used this as the voltage of the hot plate, the voltage at the hot plate, and the current through the hot plate. We're going to be really careful labeling all of these. That will get us the resistance of the hot plate, because there's another resistance in this problem. We have to be really careful. The resistance of the hot plate is, in fact, 13, and we'll go ahead and round up, 13.5 ohms. That's the resistance of our hot plate, and I propose the resistance of the hot plate depends on the temperature of the hot plate, but it doesn't depend on the voltage that we're putting across the hot plate. And we could do some experiments for that, but I don't want to do those things. I don't want to get distracted from my goal, which is to understand what the resistance drop is of this wire right here. Now, I'm arguing that there is a voltage drop across the wire, and I'm going to actually say that that voltage drop across the wire is 7 volts. We could call it 7 volts. Yeah, let's do it. Let's say that there's a look at when it's on, there's a voltage drop of 7 volts. Now we can use Ohm's law and say the voltage drop in the wire is the current in the wire. Just remember, that's the same current as the current through the hot plate because of diarrhea. But we're going to take that current and we're going to multiply it, but not the resistance of the hot plate, but the resistance of the wire. See, now we can find the resistance of the wire. This is the resistance of the service wire that's getting our electricity to us. And we could just take some voltage. Oh, we're gonna use the voltage drop in the wire, which is 7, and we're gonna divide that by the current that's going through the system, and that current is 8.40 amps. Well, thank goodness the resistance in the wire is a lot less. I get 0.83 ohms. Thank goodness the resistance in the wire is a lot less than the resistance in the hot plate. Now some people find that surprising. They think, well, the resistance in the wire should be more because the wire is not heating up, right? But the hot plate is. But remember, there's current going through the wire and the hot plate, and the current is the same through the wire and the hot plate. We want the heat to be dissipated here. So if we're using this equation for power of joule heating, we could get I squared times R. This is the preferred method of finding out how much your wire is getting hot. You take that resistance right there, it's small, and you multiply it by current squared, but whoa, those wires would eventually get hot. And I know when I'm cooking pancakes, sometimes those wires get hot. Woo-wee! But if I've got a resistance that's much more, this is a much more significant resistance, it seems like the resistor of this hot plate is going to get hotter than the wires. And thank goodness, because if I run this for a minute, I've got just about enough heat to light paper on fire immediately. And sometimes there's ground up paper in your walls and you don't want fires in your walls. I don't know, do you? I don't. Great, so let me take you a little bit further on our journey. It'll go back up to 120 again, all right? You see 120, and that I'm gonna call the voltage when there's no load, but the voltage is dropping when there is a load because I've got something like internal resistance. It's equivalent in concept to Hello boys and girls, today we're gonna talk about one of my favorite things, the hot plate. What I'm about to do is plug in this hot plate to a kilowatt power meter. But before I do so, I want to record, dang it! You can't put an announcement on when I'm making videos. And I've already turned it on, and I want you to notice that the voltage will drop. Oh my goodness, that sucker dropped. I'm gonna say the voltage on then is 113 volts. You see what I'm saying? But what stuns me is I can unplug this and internal resistance of a battery. So there's some pushing that the utility is doing, and I guess the utility is mostly doing that pushing at the transformer, or maybe even earlier in the power generation. But let's think about the transformer as a place where the utility is putting out 120 volts. So if there's no load, then I'm also... Thanks. First, I want to note the voltage of the outlet when the appliance is off. So that would be unplugged. And I'm only going to do 3 sig figs here. So I'm going to call this 120 volts. Cool? And then I'm going to plug this sucker in.